anybody. But I thought maybe I'll go over that one quickly today, since there seems to be a lot of problems with it. This is the one where two people are sitting in a canoe.
So I worked for like an hour and a half trying to get it. Yeah.
One of them is Eric, and the other one is Angela. And then there's the canoe here, the mass of the canoe. And somewhere over here there's a sunken log. So here's the scene beforehand, and let's see, relative to the center of the canoe, Angela is D over 2 toward the log, and Eric is D over 2 away from the log, as I remember it. And this was 3 meters. I'm not going to put in the numbers here, but that's the general way of doing it. So centered about the center of the canoe, one of them was D over 2 to the left, to the right, and the other one was D over 2 to the left. And we want to know, first of all, what is the center of mass? Oh, and then the two people changed places, and the canoe moved a certain distance, and he's supposed to figure out how much he weighs from how much the canoe moved. That's the story.
And how much Angela weighs?
Yes.
We have also the distance.
Right, so this is what we're trying to find.
Okay.
And the book, the picture had set it up in a little bit awkward way so that everything was to the left of the log. Well, that's perfectly fine. Let's measure x in this direction, then starting at the log. And now, what's the basic physical point in this problem? As they change places, there are no relevant external forces acting on them. Of course, there's gravity and normal force, but no horizontal forces acting on them, assuming that the water is completely frictionless. And therefore, the position of the center of mass of the whole system, all 3 of them, the canoe, Angela, and Eric, the center of mass of the whole works, has got to be fixed. So the idea of solving this is write down the center of mass position first in this configuration, then after they've changed places, and set those 2 numbers equal to each other. See what you get. The problem, I think, more than anything else, is how to set this thing up. Let's say that the original distance from the log to the center of the canoe was L. Then what is the center of mass of this system? First of all, I've got the canoe, and it's over at a distance L, by definition. And then there's Eric, and how far is he from the log? L plus D over 2. And then there's Angela, and how far is she? Well, minus D over 2. And to get center of mass, then I'm supposed to divide that by the total mass, MC plus MP plus M. Okay. So that's the situation before they change places. Actually, as they change places, assuming that he's heavier, which way is the canoe going to move? He goes over here, she goes this way. So basically, weight of people has shifted to the right, weight of canoe must shift to the left. So let me draw the scene here afterward. It looks something like this. Here's the log, and the center of the canoe. And now he is over here. So that's Eric, and she's over here. That's Angela. Still a distance D over 2 on either side, because that was where the bench is. And now, meanwhile, they tell us that the boat has moved over a distance called, let's call it S, compared to where it originally was. So it's moved a distance L, a distance S relative to the log. Does that make sense? So this is the scene afterwards, before they change places, and after they change places. center of the canoe has moved over a distance s, which they told you is the output of a different number for each person, of course. So what's the center of mass now? The canoe, first of all. How far away is it? L plus S, huh? Eric, he is L plus S minus D over 2. Angela, L plus S plus D over 2. Make sense? And then divide the whole thing by the sum of the masses. So that's the center of mass afterwards, and that center of mass, wherever it is supposed to be the same in both configurations. Center of mass does not move. And that tells me, well, that these two expressions have got to be equal. Of course, the denominators are already equal, so I don't need those. MC times L, mass of the canoe times L, plus I'll multiply these out because I'm going along. ME times L plus ME times D over 2 plus MA times L plus, whoops, L minus MA times D over 2 equals MC times L plus MC times S plus ME times L plus ME times S minus ME times D over 2. I think part of the problem with this one was that people lost their nerve at about this point, thinking it can't be this complicated, but it really is. Okay, plus MA times L plus MA times S plus MA times D over 2. Now some cancellations really do take place. Let's see. I've got MC times L over here. ME times L. MA times L. Notice that L has completely disappeared from the problem now, thing too, because they never told us how far the canoe was from the stick. All they said was that it changed its location relative to the stick by that amount. Anything else cancel here? ME times D over 2. Well, here I've got an ME times D over 2 with a minus sign. If I pulled it over to the other side, it would just be ME times D, so I can kill that. Here I have MA times D over 2. I have made a mistake. Oh no, this is on one side and this is on the other side with a minus sign. So if I bring that over here, it'll kill the 2 in the denominator. And everything else I think stays. So what's the answer here? I'll rewrite this. ME times D. ME times D, that's all I got on that side, is equal to MC times S plus ME times S plus MA times S plus MA times D. What was I trying to find here? MA, so I see that there's an MA here and an MA here. So let me get all the other stuff over to the other side. I see ME times D minus MC times S minus ME times S equals MA times S plus D. Divide through by that and I get MA equals ME times D minus S times MC plus ME divided by S plus D. There it is. So it's not a nice problem, but the physics of it was very simple. The physics was center of mass does not move. Setting it up, I think, was the trickiest part. In particular, what are you going to use as your origin? Where do you measure your center of mass with respect to? I think the log is the natural place, but you don't have to do that.
So again, why does center of mass doesn't?
The center of mass does not move because there's no external force in the horizontal direction. And remember last time I derived this general formula that dp, let's see, where I've written it is, m the total mass times a, the acceleration of the center of mass, is equal to the sum of the external forces acting on it. And if there is no external force in the horizontal direction, then the acceleration of the center of mass must be zero. In other words, the center of mass is moving at constant velocity. But wait a second, center of mass wasn't moving at all originally, so it must still be not moving. So actually, you're right, the logic behind that is a little bit complicated. But the general rule is if there's no relevant external force acting on the system, and the center of mass was originally at rest, then it stays at rest. Any questions about that one? As I say, I don't think the physics is terribly deep, but the algebra. Well, today I wanted to show you one last example, last application of the concept of momentum and momentum conservation. This is the theory of rocket propulsion. The basic calculations are done in a book, but this is, to my mind, a kind of elusive subject. I have to relearn rocket propulsion every time I encounter it. So let me try to explain to you what the basic idea is. It's all built on the notion of recoil. So let me remind you of recoil. I actually did a simple example a while ago of somebody on the ice skates holding a snowball, and then the person throws the snowball goes that way, they recoil back this way. How come? Basically because of conservation of momentum. So here's the person. Draw the scene afterwards. The person on ice skates here, recoiling backward at speed v, and let's give them a mass m, after having thrown a snowball, which has mass little m, and it's going at speed w. So, question, what's the recoil speed? V. Answer, conservation of momentum. That's not the answer, that's the physical principle involved. Momentum before she threw the snowball was 0 because she wasn't moving. I said she was at rest. Afterwards, there's momentum to the right, hers, mv, and there's momentum to the left, mw. And the sum of those must be equal to 0 because that was the original momentum. So that tells me that mv is equal to mw, or v is equal to little m over capital M times w. So that's the recoil speed. How do I get it? Conservation of momentum. This is the whole idea behind rocket motion. What a rocket does basically is throws a whole stream of snowballs out the back window and recoils in the forward direction. That's the idea of rocket motion. Actually, we call it exhaust, although that's always seemed to me bad word for it because exhaust sounds to me like something that's wasted. It's not something that's wasted, it's doing the whole job here. Throw a stream of snowball, called exhaust in the business, backward, and the rocket recoils forward. It's exactly the same principle as the person throwing the snowball. It's except a little bit more tricky. Why? Well, because it doesn't start at rest, except at the very beginning, the rocket was already moving at fairly high speed when it expelled the next snowball in the line. So the rocket was already moving. Moreover, the rocket, as it uses up fuel, gets lighter and lighter. It gets going faster and faster. Those are all obvious facts. A less obvious but subtle fact is that I need to decide how to measure the velocity of the snowballs as they leave the rear end of the rocket. How are they being expelled? Well, there's some kind of an engine in there that throws these things out the back window. How fast does it throw them? Well, presumably the manufacturer has made an engine that will expel exhaust at a certain speed. Speed relative to what? Here I was talking about speed relative to the ground. But I don't think that's going to be the relevant feature. When a rocket is going along at a high speed, it's velocity of the exhaust relative to the rocket that's really going to be relevant. That's what the motor is designed to produce, a certain velocity relative to the rocket. So when we come to do the analysis, we're going to have to switch over so that the velocity we're talking about, the velocity of the expelled snowballs, is referred to the rocket rather than with respect to ground. That also makes the calculation a little bit trickier. But the idea is basically throw a stream of snowballs out the back window and allow the rocket then to recoil forward. Notice, by the way, I hope that none of you are under this misapprehension, but a lot of people think that a rocket works because it pushes stuff out the back and that pushes against the air that's out there, and that somehow or other makes the rocket go forward. That's nonsense. Of course, a rocket works perfectly well if there's no air at all. In fact, it works much better if there's no air behind it, because then there's no air resistance on it. So it's not. I mentioned that, as I said, not because it's likely to be something that confuses you, but it is something that confuses almost all lay people as far as rocket propulsion or jet propulsion is concerned. So you ought to be aware of it, because sometimes somebody's going to be telling you some story that's based on that misunderstanding, and then you have to stop them right there. You don't understand how rockets work. Okay, let's set it up now. Here's the scene at some moment in the rocket's flight. There's the rocket. It's moving along with speed v, and it's got a mass, capital M. Both v and m are going to be functions of time. As it spits fuel out the back, its mass is going to decrease, and presumably its velocity increases. But here's the scene before, and now I'm going to watch the process when it expels the next little lump of snow out the back. So here it is. And it's now going a little bit faster. Let's call it v plus dv. And it has meanwhile expelled a lump of snow, exhaust, in the amount dm. That's the mass of the stuff that it's expelled. So its mass is now m minus dm, because it's through dm of the back window. Now, how shall I represent the velocity of that expelled snowball? This is the whole subtlety in the calculation. What is the mass of this, the velocity of that thing? Well, let us call u Let u equal the exhaust velocity, we'll call it. The speed of the exhaust relative to the rocket. Because that's what the motor is going to determine. Well, wait a minute. Relative to the rocket before the expulsion or relative to the rocket after the expulsion? Because the rocket's moving at a different speed. After the expulsion. I says, actually, it doesn't matter, but it makes it a little cleaner if you define it this way. Relative to the rocket after. So, the velocity of this thing relative to the rocket in this scene is u. So what is the velocity of that lump relative to the ground in the second picture? Well, if it hadn't been expelled with any velocity at all, it would still have the velocity, it would have a velocity v plus d, dv, that's if it wasn't moving at all, but it was thrown out the back, I mean, what if it wasn't moving relative to the rocket at all? It was thrown out the back with a speed u. So its forward velocity is evidently v plus v dv minus u, the expulsion velocity. Does that make sense? Now somebody's going to say, what do you mean? You're telling me that the exhaust is going in the same direction as the rocket? Well, I don't know. You know, after the rocket's been going for a while, that's probably going to be the case. That the exhaust, even though the rocket is throwing the exhaust out the back window as fast as it possibly can, it's going so fast itself that that exhaust is still going in the forward direction. Could well be. Of course, that's not going to be true at the very beginning. When this thing is just getting off the ground, then the exhaust is going to be going in the backward direction. But you know what? I'm not committing myself to either one. This number could be positive or it could be negative. I don't care. But I'm just, for the sake of argument, I'm going to call the positive direction to the right so that everything is consistent. And then the velocity of this lump relative to the ground is the velocity of the rocket minus the relative velocity, the exhaust velocity, which is defined relative to that final velocity of the rocket. Got the picture? To my mind, this is the whole problem. No, it's not deep or difficult, but figuring out exactly how to represent the velocity of the exhaust is the whole trickiness of this problem. Now, actually, everything is on the table. The rest is just conservation of momentum. Conservation of momentum, and a little bit of nasty algebra again. What do I have? Initial momentum, mass of the rocket, times the velocity of the rocket. Well, the rocket plus the fuel. Okay, final momentum. First of all, there's the rocket. That now has a mass minus dm, and it's going at a speed v plus dv. Also, there is the exhaust. dm is the mass, and its velocity is v plus dv minus u. Did I get the sign right? Why is this positive? Yes, it is positive because I was defining here, this is the velocity in the direction to the right. Might actually be an intrinsically negative number. At the start of the flight, it certainly is. Maybe the flight probably is not. So far, so good? Okay, I'm sorry, I had to multiply all these things out. So capital M times V plus capital M times dV minus little v times dm minus dm times dv. Now I come to this one. Plus v dm plus dm dv minus u dm. Now, with any luck, there's some cancellations. dm dv with a minus sign and with a plus sign. v dm, minus sign, plus sign. Capital MV. Conclusion, not too bad. This minus this is equal to 0, or in other words, u dm is equal to m dv. For my money, that's the essential equation governing the motion of a rocket. In the book, I think in this book, you'll find they're traditional to say there are two rocket equations, rocket equation number 1 and rocket equation number 2. I don't know. They both emerge from here, and actually this is nothing but the statement of conservation of momentum in this rather subtle context in which both this thing was originally moving. I'm taking account of the fact that its mass is decreasing and that the thing that was expelled out the back was expelled at an exhaust velocity measured relative to the final velocity of the rocket. Okay, u dm equals mdv. Let's suppose that this whole thing took a time t. Of course, I'm not really imagining that there are individual lumps. No rocket operates that way, individual lumps, but a constant stream. But dm was the amount of mass that was expelled, let's say, in a time delta t. Divide this equation by dt, and I see u times dm dt is equal to m times dv by dt. dv by dt, that's the little increase in velocity divided by the time it took to do it. What would you call that? That's nothing but the acceleration of the rocket, right? So I have on the right-hand side ma. Very interesting. That's like F, like a force that's acting on here. Whatever is on the left-hand side evidently functions like a force pushing, just as though somebody pushing on the rocket from the outside, although this is all internal. But mass times acceleration, I want to interpret the thing on the left as the equivalent force. What do you make of dm by dt? That quantity, dm by dt, that would be the amount of mass per unit time that's being tossed out the back, right? We might call that the rate of exhaust, but I don't want to confuse that with the speed of exhaust. So let's introduce some new quantity to that. That also is determined presumably by the manufacturer. So I'll call that capital R because the rate is the mass. The mass per unit time exhausted, in other words, dm by dt. So what's my formula down there say? U times R, that's the speed that the exhaust goes out at with, and R is the amount, the mass per unit time, is equal to ma, which I say is mass times acceleration. This functions as a force. We call it the thrust. Thrust is the sort of force equivalent of the rocket motor. That's determined by the manufacturer, right? The manufacturer tells you how fast this stuff is going to go out the back window and how much it plans to throw out the back window per unit time. Once you know those two, you can figure out what the force driving the rocket forward is. I think that's what's usually called rocket equation number 1. Let's come back to this equation here for a moment. By the way, you know, when I first studied, I hate to impose on you things that confuse me, but sometimes if it confused me, maybe it's likely to confuse you too. When they kept talking about exhaust, I was thinking to myself, you know, what's exhaust got to do with it? In a car, exhaust is getting rid of the junk you didn't want, you know, it's got nothing to do with the propulsion mechanism, it's a waste. But here, exhaust is the name of the game. That's what we're doing. We're trying to throw stuff out the back of the rocket. That's what's making the rocket recoil forward. So again, I think that the word exhaust is very misleading in this business. It's not some little byproduct. It's the whole name of the game. The point of the engines is to get this stuff going out the back window as fast as you possibly can. Okay, this is actually bad notation here, or rather redundant notation, because dm, the amount that went out the back, is actually the decrease in the mass of the remaining mass of the rocket. That here, of course, to figure out what the mass of the rocket less that little package of fuel would be after it's expelled the fuel. But now my point is that dm, the change in the mass of the rocket, is nothing but minus little dm. I didn't actually need the two different masses in there. I called them two different things. I don't remember whether the book does or not, because I wanted to remind you that dm is positive. D little m is positive. That's the amount of stuff that was thrown out the back window. But of course, D capital M, the change in the mass remaining of the rocket, is actually negative because it went down. So the mass of the rocket, change in the mass of the rocket, is minus the amount of stuff it expelled out the back window. Let me put that in here and write this in a little bit better notation. It says minus U times dm. Now the mass of the rocket, change in the mass of the rocket, is m times dv. Let me divide through by dv and rewrite that equation in a more suggestive way. dv is minus u times dm over m. Now, what I propose to do is integrate both sides of this equation. This is a technique that in more advanced physics you see happening all the time. It's probably the first time you've encountered it. But, as I said, it's not, it's a nice application of calculus, but not anything fancy. Integral, I'm going to integrate from t equals 0 when the process starts to some final time t. So 0 up to t of dv is equal to minus the integral of u dm over m from 0 up to t. Now I assume that u is actually a constant. U, remember what that is? That's the exhaust speed relative to the rocket. That's fixed by the manufacturer, and I suppose it's conceivable that as the rocket gets going faster or something, the speed of exhaust changes for some reason, I don't know. But the simplest possible thing to imagine is that the exhaust speed is a fixed number. It always throws it out at 90 miles an hour or whatever. Then the u comes outside of the integral, and I just have dm over m from 0 up to t. Anybody know what the integral of dm over m is, or dx over x? That's the natural logarithm of m. So this is minus u times the natural logarithm, log to the base e, of m. And I'm supposed to evaluate that at the limits t equals 0 and some final time t. What's that do for me? Well, on the right, I've got minus log at the upper limit, that would be the mass at time t, minus the lower limit, that would be the log at mass of the mass at time t equals 0. That was the starting mass of this thing. Whoops, I forgot the u. Very good. Minus u. You know how to rewrite that difference of the logs a little bit tidier? The difference of two logs is the log of the ratio, so I could write this just as well as minus u. Well, actually, let's bring that minus sign inside while I'm at it and make it like that, and then it's plus u times the logarithm of m at the beginning divided by m at time t. That's the right-hand side of the equation. Where was the left-hand side? That was the integral of dv. Well, that's easy. That's nothing but v at the upper limit, t, minus v at the lower limit, 0. Where is this guy heading? Well, I've now got you a formula for the velocity of the rocket as a function of time. Pulling this over to the other side, it's the velocity of the rocket at time t equals 0 plus u times the logarithm of the mass at time t equals 0 over the mass at times t. What does that tell me then? Tells me the speed of the rocket at time t is the speed that it started with, plus u, the exhaust speed, times the logarithm of the ratio of the original mass to the mass that it now has. So if I know what the mass has been reduced to, I can figure out what the velocity is. By the way, remember at the beginning of the semester, when we were talking about motion at constant acceleration, and I warned you that that old formula 1/2 at squared, it's true for constant acceleration only, not for other. Here's a classic example of non-constant acceleration, the 1/2 at squared inside here because the acceleration is not constant. Well, let's suppose that I did the whole flight. So that v is the final speed, and that's v at t, the final speed achieved, and v of 0, I'll assume that it started from rest. By the way, there's a little bit of a fraud in what I'm going to do now, because if you actually launched a rocket from the surface of the Earth, there would be, in the first moments, of course, Earth's gravity to fight against. That's a different question. So you know what we're going to do? We start our rocket from a dock out in empty space where there is no gravity. It starts from rest at that dock, and now I'm watching how it takes off from there. The launch of the rocket through the Earth's gravitational field, a little bit more complicated problem. So where are we? V, it started at 0 at the dock out in outer space, and its final velocity was v. What was its original mass when the exponentials and the logarithms? I hope not too many of you, but don't get exercised about that. The reason for this is coming in a second. So now I subtract a 1, and I got mf over me is equal to e to the v over u minus 1. Or, finally, the mass of the fuel I need to carry is equal to the mass of the payload, multiplied by that, times e to the v over u minus 1. There's the formula for how much fuel you better carry to accelerate a payload with mass mp up to a velocity v if the expulsion velocity, the exhaust velocity is 0. About how much is that, by the way? What would be, as an example, suppose that you wanted to get the thing going, wanted to get your rocket going at the exhaust speed itself. By the way, that would look pretty peculiar from the outside. If the rocket was going exactly at the exhaust speed, then as it throws the exhaust out the back window, the exhaust just hangs there in midair, right? Because its exhaust speed is exactly the same. So that would be a weird thing to look at, but suppose that that was actually what we wanted for some reason. How much fuel would you need for that? Then mf is equal to mp times e to the, in this case, it would be e to the 1 minus 1. Do you happen to know what e is? 2.78. So subtract 1, that's 1.71. So this would be 1.78 mp.
No, it's 2.718.
718? Ouch. Thank you. So to get this thing going at the, get your rocket going at the exhaust speed, exactly the exhaust speed, you better load up almost twice as much fuel as payload. But in general, this will tell you how much you need for any speed. By the way, what would be the best possible exhaust speed? Suppose that, you know, you can manufacture any old motor you want. What would the best possible exhaust speed be in the sense that you would have to take the minimum amount of fuel for a given payload? Can anybody spot that from this formula? What's the best that money can buy as far as U is concerned? Everything else held constant. I think we want U as big as possible. Why? Because it's in the denominator of the exponent, so we make that a huge number. Then I've got e to the 0th, which would be 1. 1 minus 1, I wouldn't need any fuel at all. But of course I can't make U infinity. What's the best I could do? In fact, I guess practically the speed of light would be the best you could possibly ask for. So that says that the most efficient rocket, in the sense that you would require the least fuel for accelerating a given payload up to a particular final velocity, the most efficient rocket would send the exhaust out at the speed of light. That's right. The best possible rocket is a flashlight. Flashlight. That's what you ought to do. And a bunch of flashlights out the back, and you would have the most efficient. Unfortunately, flashlights don't throw a whole lot of stuff out the back, so it would take a long time for that flashlight to get your rocket going at any kind of speed. So if you're worried about the time it takes, then a flashlight is good. But if you're just worried about minimum fuel, flashlight is the best rocket.
That also raises the question of useful payload, because you counted everything as payload that's
Yes.
left over when the fuel is gone. In this case, it would be mostly very exclusive batteries.
Good point.
So,
No, but in the last gesture, I'll throw the batteries out the window.
yeah,
But not at the speed of light.
that's good.
Good point. This is scratching the surface. Let me tell you one last thing, because I mentioned a while ago that conservation laws will give you a very quick answer to many problems, but they do not tell you mechanism. And this is a very good example. I was always bothered by rocket propulsion. Why does that rocket go forward when I throw the exhaust out the back window? It's not obvious. I know that it's got to because I believe in conservation of momentum. But why? What's the mechanism? Here's the rocket again, and let's examine the combustion chamber there. What's going on in the combustion chamber? Well, I'm burning fuel and there's hot gases all around. here's one particular molecule. That's molecule A, and it happens to be heading out the back door anyhow. What does that do to accelerate the rocket? Nothing whatsoever. But how about molecule B next to it that happens to be going in the forward direction? How does that get out of the back door? Well, it has to come up here, bounce off the front plate of the combustion chamber, and then gets expelled. And that's what pushes the rocket forward. It's the half, roughly, the half of the molecules in the combustion chamber that happen by good fortune to be going in the forward direction have to bounce against the front of the combustion chamber, delivering an impulse to the rocket, and it's a combined effect of all of those molecules that actually pushes the thing forward.
And the impulse delivered by a molecule going forward, in order to go backwards, is exactly twice the average momentum.
Very good.
The ones going back count.
So,
Yeah, the right
you can
answer.
either count that and say every molecule delivers mv, or you can be honest about it and say half of them don't do a thing, and the other half deliver 2 mv, and you're going to come up with the same answer. Very nice. Next time we start rotational motion.